Hello and welcome. This time after a bit of a break, but it's worth the wait because today we are going to talk about one of the most important concepts in modeling. We're going to talk about how to model indifference. In particular, we're going to talk about one very important approach, the Jeffrey prior. I had the very strong impression that there's a lot of structure missing in my videos, so I'm going to try my best to be more orderly and to have more subsections with well-structured outlooks. So I'm going to start with that now. So what are we going to do in this video? First, I'm going to talk about the actual problem. What is modeling? What do I mean by modeling indifferences? Why is it important? Basically, this is going to come down to how do we deal with a problem where we have no prior information. I'm going to show that for the continuous case, this is a very tricky question. And I'm going to show this on two examples, which are going to be a subcategory of their own, which is the topic of having a prior, which is invariant under a group of parametrizations. I'm going to talk about how the distribution of a prior changes under a reparametrization. Therefore, I need to introduce the transformation formula, which is a quite common result. If you've had a couple of analysis courses, you probably know of it. And I'm going to talk about the version for distributions. I'm going to use this formula to show that we have a real problem with most choices for kind of indifferent priors, and that we actually need a mechanism to choose such a prior. And this mechanism for choosing such a prior is going to result in choosing the Jeffrey prior based on the sampling distribution. The Jeffrey prior is not easiest to calculate, by the way. Definitely butchering the name. Very sorry to whoever designed this prior. If I'm butchering the name, which I'm definitely doing, please call me out on it, and then I can correct it at least in the next videos. But for now, I guess you have to deal with my pronunciation. So anyway, the Jeffrey prior is difficult to calculate, so I'm going to talk about one subset of prior distribution which we already know of sampling distributions which we already know of, the natural exponential distributions, and I'm going to derive a formula where, at least for exponential distributions, we have a pretty easy way to calculate the Jeffrey prior. I'm going to show some examples with this, but then I'm going to have to point out that at least for the multivariate case, there's some serious issues with choosing the Jeffrey prior, and I'm going to show some examples. I'm also going to show one attempt to resolving this issue, but in general there are many. I'm going to finish with a short summary of what just happened. It's going to be a very long video, I'm afraid, and a little bit of an outlook at different ways to model indifference, which also exist. Alright, so let's get started. So why do we care about modeling indifference? And also, what do I mean by indifference? So imagine we talked about the last video where we talked about conjugate priors. We talked about how to basically choose priors when we have at least some idea on how our hidden parameter theta behaves. Where are some positions where this parameter is most likely, where what is there like some area where we know, okay, it's pretty unlikely that it's here, but it's rather likely that it's in this position. But sometimes in life we are not so lucky. Sometimes we have no or practically no information. Sometimes we deal with a completely new topic where we start from scratch and we just don't know anything about theta. Still, we want to make statistical inference. So I chose this topic, I called it modeling indifference. Indifference is not the expression that I saw when I was looking at this topic. It was more something like, okay, what do we do when we have no prior information? But I thought it was a decent name, because essentially what we have when we have no prior information and we have some parameter space is, we say that no matter what value we have, so let's say we have some parameter space big theta, and no matter what theta is, we have the same confidence in any value of theta. This does not only have to be the case where we have no prior information. This can also be the case where the evidence is equally strong for every single case. So I've already resolved the question actually for one case, the discrete case. In the discrete case, we can just say the probability of theta being equal to some value theta 0 it's the same for any single value of theta. So this implies that this probability is one constant value. In other words, it's proportional to 1. So we can just say that this is proportional to our prior distribution at theta 0 for any theta 0 in the parameter space, which in this case is discrete, so it goes like from theta 1, theta 2 and so on. Could be finite, could be infinite. There is one difference between the finite and the infinite case. For the finite case, we have the uniform distribution. For the infinite case, you notice that there's no way that all of these values can possibly sum to 1. We say that pi is improper. The concept of improper priors deserves a video on its own, and it's going to get one. For now, we just say that if we have an improper prior, that is, we have some density where the integral over this density, or in this case the sum, does not equal 1, or in particular it equals infinity, because if it equals some constant we can always normalize it, but if it's equal to infinity there's nothing we can do. But as long as we can still derive a proper posterior, we are just going to say that this is okay. The proper posterior can just be derived by Bayes' rule, if it's possible to do that. So we can use this rule to derive a posterior. However, it's not an actual posterior in the usual sense, just because our prior is an actual prior in the usual sense. There's going to be many rules that in usual probability theory hold that these improper priors are going to break, and they're going to break them heavily. You're going to see one example today, and one important example. There's going to be many, and you're going to see them in the video, but one important example is that improper priors do not, that estimators based on improper priors, so Bayes estimator, does not have the very nice properties that we discussed in the video about Bayesian estimation. Nevertheless, we're going to see very shortly that improper priors are the only priors fulfilling certain properties which we're going to need if we really want to model indifference. Anyway, we've actually solved this already for the discrete case, but we also see this for the continuous case. Even though our prior is improper, it still fulfills our demand that we have the same value, the same confidence, quote unquote, for every parameter of theta. In the continuous case, even with improper priors, we are given a very hard choice. In fact, this whole video is going to talk about how on earth to deal with the continuous case. And there are many different approaches. All of them are quite complicated and none of them are really satisfactory. One naive guess would be to take the uniform. We're going to look at what happens if we do that. It's kind of it's a nice approach. Okay, it worked for the discrete case, even in the infinite case, let's try it. In the continuous case, sometimes it works, but sometimes it makes less sense. So the topic is invariance under a group of transformations, and the uniform is a particular case of this. Let's say we have that the parameter space theta is just equal to the whole real space. Then we could say, since we are indifferent under each of these parameters, it must make sense. We could kind of say theta we could say is kind of a location parameter. And so we could say if we shift the location, our distribution based on theta should still be the same. So what I'm saying is that theta plus mu should have the same distribution as theta for every value that mu can take. What does it mean in distributions or in PDFs? Since we're only going to talk about the continuous case today. Well, we want a distribution of theta plus mu. You can calculate that this is the PDF pi. If we have the prior distribution in theta, we have the PDF pi in theta minus mu. This should be equal to pi in theta for every theta and for every mu. In particular, this must hold in the case that mu is equal to theta. But this implies that pi of theta is equal to pi of 0 for any theta. But it's proportional to 1. And this defines the continuous uniform distribution. Okay, so that's really nice. We've seen that the uniform is actually the only distribution that is what we call translation invariant. And maybe that's a property that we want to have. But there's another case which is equally convincing, where we have that theta is not equal to the real space, but it's some positive number. Here we could, for example, say we have some numbers given, but we don't know the scale on which these numbers are. So no matter what the scale is, we should still have the same confidence on every single number. In other words, we want lambda times theta to have the same distribution as theta for every positive value of lambda. Again, we can rewrite this in PDS. For scaling, you can quickly find out that pi of theta transforms to 1 over lambda times pi of theta divided by lambda. In particular, I should say this holds for every theta and for every lambda. In particular, it holds for lambda equal to theta. But this time we have that pi of theta is equal to pi of 1 times 1 over lambda. 1 over theta. Which is proportional not to 1 but to 1 over theta. And that's not the uniform distribution. So we can already see that this case, the case of invariance under scaling, is not met by the uniform, but for this other distribution, which has the PDF 1 over theta, which is of course improper because you can't integrate this from 0 to infinity. These two are a special case of just the case that we want invariance under some kind of transformation. So let's say we have some group of transformation, sigma, where each element is some transformation from theta onto itself, where we demand at least that sigma is a bijection. And we want that small sigma of theta to have the same distribution as theta for every sigma. This, of course, doesn't always have to be the case, but we can say that there's some scenarios where it makes sense, like this scenario with the scaling, where we can say, okay, we don't know the scale, so no matter what scale we have, we should have the same confidence. In this case, it makes sense to go to this approach, and this approach actually has an own chapter in the textbook, where they talk about stuff like the invariant harm measure and so on. So if you're interested in this topic, I recommend checking out the textbook. But I'm going to move on to another special property. However, I'm going to pick up this topic again shortly for the Jeffrey prior, because we'll find out that quite often the Jeffrey prior actually incorporates these groups of transformations automatically. I'm going to move on to not invariance under a group of parametrizations, but invariance under transformations, in particular under reparametrizations. You can see that for these two, I just said that I have a formula on how they behave under transformations, but really I should tell you the formula so that you know how they behave. So let's move on to that. The formula, coordinate transformation formula, as I said, you probably most likely know it. It's given for a very general function, tau, which goes from theta to somewhere else, it doesn't matter, to its image. And this is a reparametrization. So in mathematics, it's enough to say that this is a diffeomorphism, which just means that this is differentiable, invertible, and its inverse, it's also differentiable. In this case, we have this very powerful theorem. For any such tau, the PDF of tau theta is given by, let's call it pi 2 of psi, which is equal to the inverse, so to pi, let's say pi 1, of the inverse of tau of psi times the determinant of the Jacobian of tau's inverse in psi. And here we take the absolute value. Where pi 1 is just the prior, so the distribution of theta. So this has a consequence. We've already saw this. We already saw this in the last video. We already saw this in the last subsection. But I want to formalize this, and I want to show a really nice example. So let's say we have some theta, and that's just the vector of probabilities that we collected from some data set. And we don't want to express these probabilities by their direct value, but instead we want to give their odds ratio. The odds ratio is defined as the ratio between theta and 1 minus theta. It's very common to express probabilities this way. That's why it's a very nice example, because people definitely do this sometimes. And you could say sometimes we don't. So let's set this to tau of theta. If theta is uniformly distributed, so if pi of theta is equal to 1, then we can use the transformation formula to immediately give the distribution of this reparametrization, because this formula here is equivalent to theta being equal to tau of theta divided by 1 plus tau of theta. In other words, the inverse of psi of theta for some psi in the image of tau is psi divided by 1 plus psi. The derivative, because it is the Jacobian in the one-dimensional case, is 1 times 1 plus psi minus psi times 1 divided by 1 plus psi squared. So it's 1 over 1 plus psi squared. And this immediately implies that by the transformation formula, tau of theta, even though we should give the same distribution to this equivalent formulation to these probabilities, which is just convention. It depends on which department you are, if you want to use this. This has the density, sorry, I should say, it has the PDF pi 2 of psi. I guess I should have called the first one pi 1. I'm talking about pi 2, which is pi 1 of the inverse of tau in psi times the derivative 1 over 1 plus psi squared, which, because this here is equal to 1, is just equal to 1 over 1 plus psi squared. And that is not uniform. And that's a real problem. So how do we deal with this? It turns out that there's a very elegant solution to this, and that's the Jeffrey prior. The Jeffrey prior is defined as an interesting balance between, actually you could even say a difference between Bayesian statistics approaches and frequentist approach, because I think one way, I'm not sure if this is the actual motivation, but I think one way to think about this is to say that the Jeffrey prior counters an intrinsic weight that the sampling distribution has on each information. There's a measure called the Fisher information. Maybe I should start with this definition. Is defined as the variance of the derivative of the log likelihood with respect to theta for any given theta. It's a function with respect to theta. This is a frequentist measure, and it's used, for example, to derive the Cramer-Rao boundary and to derive the approximate distribution of the maximum likelihood estimator. It's also a measure of how much information a model gives about theta, roughly speaking. I'm not sure if I'm giving this right. I do not have a lot of experience in the subject. But it's nice to see that if we see this as a kind of intrinsic motivation that the model gives about theta, then it makes sense that we define the Jeffrey prior as proportional to the Fisher distribution. Kind of. We say that the Jeffrey prior is given by the square root of the Fisher information. We can define both of these for the multivariate case, where for the Fisher information, instead of the derivative, we take the Jacobian. And for the Jeffrey prior, instead of the square root of the Fisher information, we take the square root of the determinant of the Fisher matrix in this case. Because this here is the variance covariance matrix. It's a matrix. The Jeffrey prior, I should say more precisely, the process of choosing the Jeffrey prior is invariant under reparametrizations. There's a very nice article on this in Stack Exchange, which I'm going to link in the video. So what am I saying when I say the Jeffrey prior is invariant? The process of the Jeffrey prior of choosing the Jeffrey prior is invariant under reparametrization. I'm saying that if we have some value theta and we assign this data set the probability distribution pi of theta, let's say pi 1 of theta, then the information that this value gives about this reparametrization, so let's say the distribution of tau of theta pi 2 of xi is the Jeffrey prior which we would choose for xi. Also, apologies for the x's, I'm not the best in Greek handwriting. Already been harshly criticized for that. Why is this the case? Well, let's say we have this case, then we know the distribution of xi. It's equal to the value of pi 1 in the inverse of tau in xi times the absolute value of the determinant of the inverse of the Jacobian of the inverse of tau. So what happens if we choose the Jeffrey prior? I'm going to zoom out for this. Well, we know that pi 1, if we choose it as the Jeffrey prior, is equal to the Fisher information based on our sampling distribution, I1 of theta, which is equal to the variance of, this is called the score function, this part. Not that it matters. This is not the same as the Fisher information which we get for xi. We're going to find out that the pi 2 here and the what I'm going to define soon are the same. So I'm just going to abuse notation here for a second. The Fisher information that we will get for xi is different. It's the variance with respect to xi of this derivative. And actually I want to do it for the multivariate case, so instead of derivative we write the Jacobian. But what is this sampling distribution? Well, the sampling distribution doesn't really change under reparametrization because we condition on xi or we condition on theta, but xi, which is just tau of theta, it gives you exactly the same information because this here is a bijection. As I said at the start, it is a diffeomorphism for the transformation formula, and diffeomorphisms are in particular transformations or bijections, they are bijections. So this here is the variance with respect to psi, which is tau theta, of the Jacobian with respect to psi, of the logarithm of f of x given theta. Doesn't matter if we have psi or theta here, but theta is just the inverse of tau of psi. This is just one major fact about conditioning. If we have a bijection going back and forth, we still get the same information. Now we have the Jacobian with respect to some function, which has some function in it, and both are differentiable, so we can use the chain rule. So this is the variance times the Jacobian with respect to theta, so this is the same thing, of the log likelihood, times the Jacobian with respect to psi of the inverse of tau in psi. So you're already starting to see what this looks like. But the variance, it's first of all, this here is not a random variable. This is constant. The variance transforms very nicely under multiplications with constant, even in the multidimensional case. This is just equal to the Jacobian transposed times the variance with respect to theta. Again, it doesn't matter if we have variance with respect to psi or theta, is the same. Of the Jacobian of the log likelihood times the Jacobian of the inverse. But now we're done. Because this here, it's equal to the original official information. So our pi2 here, I'm going to write above, is equal, well, we've already seen this, so this is just, so the inverse of psi, it's theta, so this is just I1 of theta times the square root of the determinant of this thing. So actually we have the absolute value of the determinant, but this is the same as the square root of the determinant of the variance. So yeah, sorry, I should rewrite this. So this is actually the determinant of I1. The square root of the determinant of I1, and this here is wrong. That's not pi1 and pi2. They are then again the square root of the determinant. So this is pi1, and then we have the square root of, which is just, so this part is the same as the absolute value. So in total we have this shape, which is exactly what we wanted to show. Sorry for the mistake down there, I hope it still makes sense. Okay, so now that we know that it's invariant, how do we calculate it? And that's the next topic. So much about the topic of straight lines. The Jeffrey prior for natural exponential families is quite easy to calculate, but I want to prove very thoroughly why it is easy to calculate. So remember, for natural and exponential families we have the following form. We have the exponential function of e to the power of theta times x minus some function psi times some measurable function h. H is usually not very important. We're going to focus on regular exponential families. So we're going to focus on the case that the parameter space theta is an open set. For this case, we can quickly see that the Fisher information is just the variance of x. Since we have a derivative with respect to theta, h of x is going to disappear. And we're left with this, but remember, theta is a constant given theta, and the variance does not care about constants. So this is just the variance of x. This can be calculated rather easily using the function psi. This is in fact equal, I'm going to focus on the one-dimensional case here, to the second derivative of psi in theta. And I'm going to show this. And I want to be quite thorough, so I'm going to show that psi is actually differentiable, which takes quite a few steps. So first of all, let's look at something like the moment generating function of x. We're going to first look at the moments of x. So we're going to look at e to the power of psi of theta times the expectation of the absolute value of x to the power of k for any k. We don't care, it has to be a natural number. That's equal, since the psi part cancels out, to the integral over h of x of e to the power of theta times x. And now I'm going to multiply both sides with some small value t to the power of k divided by k factorial, where we choose t such that theta plus or theta minus t is still in the parameter space. We can do this since the parameter space is open. So this integral, we can say it's actually, I'm missing something. I'm missing the absolute value of x to the power of k. This here is just a part of the power series of the exponential distribution. So we can approximate this by just taking the whole power series and saying that this is smaller or equal to e to the power of theta x plus t times the absolute value of x. But then this is equal to h of x times e to the power of theta. Let's say we want to say it's smaller or equal than theta plus or minus t, depending on whatever phi maximizes this, times x, because x is an absolute value here. But we know that this is smaller than infinity because this is just an integral over a parameter space, which we already know. What I mean is that this here, missing the constant e to the power of psi, to the power of minus psi, is just a density. So this whole integral has to be some finite value. So the expectation of not only the absolute value, but in particular of x to the power of k exists. Not only that, but by, first of all, the monotone convergence theorem, the sum, and now I'm not going to write t, instead I'm going to write theta plus t. So I'm going to interchange the argument because I want to develop in theta. So I'm going to define this function u in t equal to theta minus t. So now I'm developing, okay, I think I said plus t, I meant minus t, to the power of k factorial. And I'm going to sum over this for all values, times e to the power of psi of t. This doesn't change anything for the convergence, times the expectation of x to the power of k exists, and is thereby a power series, which implies that it's infinitely often differentiable. And this implies that the derivative of u, first of all u in theta, so if we plug this in and set this to 0, this is only 1 if we take k equal to 0, so we have that this is equal to e to the power of psi of theta. and this is also just 1, in case k equal to 0. On the other hand, the derivative of u in theta is equal to the second part, so setting k equal to 1. This gives e to the power psi of theta times the expectation of x to the power of 1, which is just u of theta times expectation of x. And then the second derivative of u is again u of theta times the expectation of x squared, because that is the case of k being equal to 2. This then implies that psi of theta, which is the logarithm of u, is differentiable infinitely often. And I'm going to zoom out again. And we know its derivatives. Psi prime of theta is, well, it's the logarithm of u, so it's u prime of theta divided by u of theta. So that's the expectation of x. Okay, here I should mention the expectation is always with respect to theta being constant, so I'm going to change it everywhere now. And also the second derivative of psi, well, that's second derivative of u times u minus the first derivative of u squared divided by u squared, which looks complicated, but you can just plug this in and get the expectation of x squared minus the square of the expectation of x. But that's just the variance. And we've just shown that this is the Fisher information. Alright, so now we know how to calculate this. Now let's look at one example and immediately one problem. So first, one example just for calculation. We had this example with the beta distribution, and I kind of chickened out of it because I didn't show it for the formula which we had for the conjugate price in, I think, 2 videos before this one. So let's show it for the Jeffrey prior. It's a bit ugly, but I think it's a good exercise. So the good thing is, or let's say the bad thing is, that first of all we have the sampling distribution with respect to p, which has a nice form, but it's not the form that we want for a natural exponential family. For a natural exponential family we get this form. So again, this is h, this is theta, and this is psi of theta. So theta is equal to the logarithm of p divided by 1 minus p. Solving this for p gives that p is equal to, well, first of all we get that exponential to the power of theta times 1 minus p is equal to p, and we can solve this for p and get that e of theta divided by 1 plus e to the power of theta is equal to p. So psi of theta, which is equal to the logarithm of 1 over 1 minus p, is just, if you just plug it in, the logarithm of 1 plus epsilon. 1 plus e to the power of theta. So the Jeffrey prior is for theta the second derivative of this, which is admittedly ugly looking. First of all, it's the first derivative of this, and then when you calculate this out, but actually I've forgotten the square root again. This here is the Fisher information, and then the Jeffrey prior is a square root of this, so it's proportional. I shouldn't write proportional here, this is exact. But the Jeffrey prior is proportional to e to the power of theta divided by 2 divided by 1 plus e to the power of theta to the power of 2, which cancels out, so we just have, so sorry, it shouldn't be power of 2, it's just 1 plus e to the power of theta. So now we can just reparametrize this distribution, or this theta, since we have the reparametrization tau of theta equal to p. We know that the inverse of tau, we've already calculated it. The inverse of tau of p is equal to the ln of p over 1 minus p. And this implies that the derivative is, so first you have 1 over p over 1 minus p. And then we have the derivative of this, which is 1 times 1 minus p plus p divided by 1 minus p squared. So a lot of things cancel out and we get 1 over 1 minus p times p. Now we can plug everything in and see that there's a free prior in p, which is perhaps more interesting, is proportional to the Jeffrey prior in the inverse of this in p times this derivative. If we plug this into the inverse, this is just the square root of p divided by 1 minus p divided by 1 plus p over 1 minus p. So here I just plug this in and now I multiply with the derivative 1 over 1 minus p times p. And this here just solves itself and we get p to the power of minus 1/2 times 1 minus p to the power of minus 1/2, which is a beta distribution with parameters 1/2 and 1/2. So actually we even have the conjugate case, which is definitely not always the case, for example for location parameters. And we have kind of this case of equal evidence of 1/2 and 1/2 for both alpha and beta. This was a lot of calculations and it's actually nothing to do with problems with the Jeffrey prior. So let's try this again and let's see if I can talk more about the actual subsection. Okay, so we've shown the calculation. Let's show one problem. The Jeffrey prior is fine, at least the textbook says it's fine. I don't actually know, but it's fine for the one-dimensional case. For the multidimensional case, it has several problems. One of them is that if theta is not the parameter of interest, the estimators that we get are very, let's say, weird and actually sometimes even completely suboptimal, which we see in our example. Say we have a normal distribution with multidimensional mean, mu, or let's say theta, and unit variance, no covariance. So we have the identity matrix with dimension p as the covariance matrix. The Jeffrey prior, because theta is a location parameter, by which I just mean that theta plus mu is still in the parameter space for any number mu. We have the case at the beginning. We know that there's only one distribution, and since the distribution family doesn't change, if we add mu, theta plus mu has to have the same distribution as theta for every mu. So without any calculation, the Jeffrey prime must be the uniform, or at least proportional to the uniform. This is an improper prior anyways. So this immediately gives that theta given x is normally distributed with mean x and no covariances. Why? Because the posterior is proportional to pi of theta, which is just 1, times the sampling distribution. But the sampling distribution, it has this weird symmetry between x in its mean. So remember, we have a product here because we have independence, and we have 1 over the square root of 2 pi times e to the power of minus 1/2 times xi minus mu I squared. So, okay, I should again, I'm sorry, I don't know why I always say mu. Actually, I know, because it's very common. But here, theta makes more sense, because you always talk about theta. But it confuses me. So, we have this, and theta and x have the same role. We have a function with respect to theta here. So, we already immediately know the distribution. We want to estimate the length of theta. And we're going to square it because then the math is much easier. So when I denote this, I mean the Euclidean norm, and the square just means squaring it. We can easily calculate the base estimator, the expectation, if you remember the last video. It's a couple of videos ago, but if you remember it, the expectation of theta, or the length of theta squared given x. It's quite easy because it's just, and we can pull the sum out, the sum of the expectation of theta I squared given x. And we can also simplify this as the sum of theta I. We would much rather have theta I minus xi, because that's its mean, plus 2 times the expectation of theta I minus xi given x times x but this is just 0, this part, because we subtracted the mean, plus the expectation of xi squared given x, so this is just xi squared. And this here is just the squared expectation of a normal distributed random variable with mean 0 and variance 1, so this is just equal to 1. And we sum this p times, so we get p plus the sum over xi squared, which is the length of x squared. So this is our base estimator, but if we subtract some other value, if we take the expectation, if we know theta, of the length of x squared minus c, and we see, okay, what's this difference with the actual value, the length of theta squared, then this squared loss gives you the variance with respect to theta of, okay, the length of x squared minus c, but it's just the length of x squared because the variance doesn't care about constants, plus the bias squared, which here is the length of x squared minus c minus the length of theta squared. And we square this whole thing. This is a very well-known formula. You can easily prove this by just writing it out. So this is equal to the variance of x squared. And then just by the same trick, maybe I'm not going to repeat the trick again. You can do this at home. This is just p minus, actually p plus c squared. So the optimal value for c, if we subtract some constant, here we subtracted some constant, actually I'm sorry, it was a minus. We subtracted some constant minus p, but really we should have p. So we should have length of x squared minus p is always, no matter what belief we have in theta, it's always better than our base estimator if we have this Jeffrey prior. And the reason for this, basically the reason is that by using the Jeffrey prior, we've broken a couple of laws. We've used an improper prior. And as I said at the beginning, using an improper prior breaks a lot of the very nice properties that the Bayesian estimator has. So here we have an example of inadmissibility, which I talked about in the videos about Bayesian estimation. And in this video I've mentioned that base estimators, it's incredibly rare that they're inadmissible, and if they are, there's another base estimator that is admissible. So this mustn't happen, and it doesn't happen if we actually have a real proper prior. But in the case of improper prior, anything can happen. So the Jeffrey prior, it has very nice properties, but we sacrifice a lot of other very nice properties that Bayesian estimators usually have when they have proper priors. So one very important thing is that we can't just think, okay, we have this nice prior, we can still make Bayesian statistics. We can make Bayesian statistics, but it doesn't quite work out. So how do we solve this? I'm going to present one way to solve this. There are many, but one simple way is to just still use one-dimensional Jeffrey priors. It's called the reference prior approach. we order the values of theta, since we're multidimensional, in values that we're interested in. So we say we have theta 1 up until theta n, or let's say theta p, where theta 1 is the most important value we're interested in, and the other values have decreasing importance. And the idea is the least important value is the one we are most indifferent about. So we take, for the Jeffrey prior of phi theta p, given theta 1 up to theta p minus 1, the usual one-dimensional Jeffrey prior, where we take all other coordinates fixed. Then you just calculate the marginal distribution of x given x1 up to x given theta 1 up to theta p minus 1. This is equal to the integral with respect to, I'm going to write theta p. I'm not going to explicitly write the definition, but I'm just saying like this is the area over which theta p can change, over f of x given theta 1 up to theta p times the chosen distribution, which I'm going to write as pi of theta p given theta 1 up to theta p minus 1 with respect to theta p. And then we just repeat until we're done. For our example, we're interested in the length, so we write the length of theta as the first parameter, because we can do that because there's a reparametrization called polar coordinates, where we first give the length of our vector and then p minus 1 angles. So these are multidimensional polar coordinates. Usually we have this for 3D, where we have 2 angles and 1 length, but you can generalize this. In 3D it's and usually we have 2D, where we have 1 length and 1 angle, but this also works. And this gives a much more interesting estimator, and it's derived in the textbook. Let's even say better estimator. Another example is for the normal distribution. I'm not going to calculate this out, but the Jeffrey prior, if we take normal distribution with mean mu and sigma squared, is, or if we take mu and theta as the parameters, mu and sigma, 1 over sigma squared. It turns out that a much better prior is produced by the reference prior approach. So let's say we want to estimate sigma. So we have that we order theta to sigma and mu. Then for mu, we again, since we have a location family, given sigma, we have that pi of mu given sigma is just 1. And then f of x given sigma, it's the integral. We don't really care that the integral doesn't exist. In the case that it doesn't exist, we take smaller subspaces. I should write this down. So one important thing I forgot to mention is that if the integral that we take for the reference prior approach is not defined, which we actually have in this case, we take, for example, smaller subspaces and take the limit. For example, if we have the real line, we take the interval from -n to n. We don't just take any smaller subspaces, but we take compact subspaces. So if we have this interval, this converges. For sets, we just take the union for convergence. This converges to R, and every integral over this compact subset, it's well defined. So this here over the compact subset -n to n over 1 over the square root of 2 pi sigma squared e to the power of -1/2 mu minus x squared times 1 over sigma squared. This integral, we can calculate it, but maybe we don't want to, because this, okay, here of course I should have multiplied this with the with this here, but this here is just 1, so it cancels out. This here still is a scale family, and I didn't really need to write down the integral to show this, because still, no matter what sigma is, if we multiply with it, so what I mean is sigma times lambda, it's still in 0 to infinity, which is the interval where sigma is, sorry, excluding 0. So we know by the first slide that we have that pi of sigma is equal, so the Jeffrey prime with respect to sigma is equal to 1 over sigma. And then we combine all of these. We say that pi of theta is equal to pi of sigma times pi of mu given sigma, which is equal to 1 over sigma, which is a much better prior. At least that's what the textbook says. Okay, let's go back. So we've gone over this very, very long journey, and we've seen how to calculate the Jeffrey prior. We've seen that the Jeffrey prior fulfills the one property which we really wanted to have, which is invariance under reparametrizations. We've even seen that 8.1, invariance under group of parametrizations, is sometimes included in the Jeffrey prior. But we've also seen that it can have major drawbacks in the multidimensional case, why, for example, we need the reference prior approach. For alternatives, go check out the textbook. It talks about alternative like the the entropy maximization prior, which maximizes the entropy, which is our uncertainty. It talks about matching priors, which are priors which are very nice from a frequentist perspective. And it talks about robustness. So if we did choose a prior, what happens if we change it slightly? And if something big happens, then maybe we should reconsider how we choose how we have chosen our prime. Alright, so as I said, this has been a very long video. I hope you came out a little bit less confused than before. I hope you could learn something, and see you next time, where we talk about how to finally apply all of the information that I've given you so far.